Hello guys, and welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today, another thermodynamic problem, but now it's more of a theoretical problem than anything else. We are to prove the relationship below. So the problem statement reads, show that during an isothermal process, that is, when T is a constant, from state 1 to state 2, the relationship between pressure and volume is PV equals constant, and the work is given by the equation below, right? So work from 1 to 2 is the integral from 1 to 2 PdV, and that's equal to P1 V1 times the natural log of V2 over V1. So we need to prove two things. First, that the relationship between pressure and volume is equal to a constant, and then we need to prove that the work is equal to this equation here. So the first thing we talk about is the ideal gas equation. PV, P times V, right, pressure times volume, equals mRT or nRT. Okay. M for mass, N for number of moles. Same equation. What changes is the unit we're going to use here for the R. So note that we have a relationship. This is the ideal gas equation, right? See, any ideal gas behaves this way, and actually it's the other way around, right? Any gas that behaves this way we call an ideal gas. And what we can do is I'm going to divide everything by the temperature. I'm going to have the pressure times the volume divided by the temperature equals the R and M. So the first thing to note here is note that unless we have mass going in or out, so unless mass is allowed to enter or leave my system, this term here, R times N, is a constant, right? Is a constant because R is the ideal gas constant, right? So it's always a constant, and the mass is the amount of mass we have inside our system. So unless there's mass coming in or out, this is a constant. Okay, and if this is a constant, note that we're saying that PV divided by T of any system, right? Then it's a constant relationship between PV and T, right? If this is true, then it doesn't matter whether this is 1, 1, and 1, or 2, 2, and 2, or n, and n, whatever number we want. This always holds true, right? So unless there's mass entering or leaving my system, this will always hold true. And then we can do star, and T star, right? It's always going to be true. Now, the second thing to note is they clearly say in the beginning that the temperature is the same, right? So the temperature is constant. So in this example that we have here, what they're saying in the problem is show that if T1 equals T2, which equals T star, etc., right? So whatever we throw at it, then we can eliminate these T's here, and we end up with P1 times V1 has to be equal to P2 V2, which has to be equal to any P times V of any state. Horrible stars, but the idea is there. So this is, how we show that P times V is always going to be a constant. Pressure times volume is always going to be a constant in a situation like this, right? Ideal gas, no mass entering or leaving, and isothermal, same temperature. Cool. So with that, we did part 1. So now let's do part 2. Let's show that work is given by the combination there. So let's start with this part here, right? Because this is the definition of work, pretty much, right? Work from state 1 to state 2 is the integral from PdV as we go from state 1 to state 2, V1 to V2. So let's rewrite that. So work from state 1 to 2 is just the integral from 1 to 2 of PdV. Okay. Now let's substitute where we have the pressure. So what I'm going to do is I'm going to literally copy this here. Okay, let me copy this and paste it down here, and let's solve for P. So let me leave P on this side here, divide everything by the volume. We're going to have P equals mass times R times T divided by the volume. Okay, and I'm going to literally substitute this into our equation. Instead of leaving out p, I'm going to substitute and put this here. So this has to be equal to the integral as we go from 1 to 2. And now where I had p, I have this, and they still have the dv there. Okay, next, note that if this is well, we already know that this term is a constant unless there's mass entering and leaving, right? So we can leave the integral. So let's just do this. Let's copy. Let's paste right here. So I can go ahead and say, okay, so if this is a constant, then it's not going to be affected by my integral, and it can go like so. Should probably leave myself more space. Okay, so if this is a constant, then it doesn't really care about the integral. It can come out. Okay, beautiful. So we're left with t and v. But you know what? T is a constant too, because it's an isothermal process, right? That's the premise of this problem. So therefore, t also doesn't care about the integral, and t can also come out without really much change. And then we're left with the integral of dv over v. And guess what is the integral of dv over v? It's the natural log of v2 divided by v1. Okay, so if we keep going on this equation, let's go downwards, I guess, so that we can keep things sorted together. Let me do this, put it here to the side, then we can go downwards. So here, if we continue this, it's going to be mass or number of moles, depending on your R, times a constant, times another constant, which is the temperature, does not change, and natural log of v2 divided by v1, right? And obviously this can be any number. In this case, it's just 1 and 2 because we started with 1 and 2 because the problem said so, right? So final state, initial state, doesn't really matter the number. Okay, and now we're almost there, because note that, we wanted to prove that this is equal to, PV times the natural log. So note that we have everything. This is looking nice. This is already what we're looking for. We just need this now. But if you recall, I actually know that already, because check this out. This is how we started the whole thing. Ideal gas law, right? And once again, I'm going to copy this. Super useful. And I'm going to come back to my equation, and I'm going to note the following. This guy and this guy are exactly the same. Right, horrible choice color. This guy exactly the same. So that means that I can substitute what I have there. I can substitute by this. Right? So if I continue on, I can say that that is also equal to, give me a bit more space, P times V of natural log of V2 divided by V1. Okay, we're almost there, because the last thing to note, and this is just, the final piece of the puzzle, is that they want it for state 1 and state 1, and that's perfectly fine. Why? Well, because it can be anything, right? It can be anything as long as both of them are the same. It can be 1 and 1. It can be 2 and 2. It can be 3 and 3. It can be star and star. It doesn't matter. Why? Because it's a constant, right? It's a constant. They're the same value. The multiplication of the pressure times the volume of any state is going to be the same value. So it doesn't really matter what I put in here. It can be 2 and 2, 3 and 3, 1 and 1, star and star, and it doesn't matter, right? It's going to be the same exact value. So there we have it. This is the second part that we're asking for. So we conclude that the work as we go from 1 to 2 equals the multiplication, the product between the pressure and the volume times the natural log of the final state and the initial state, right? So state 2 over state 1. Simple problem, yet useful exercise to understand where things come from and how to start thinking in terms of thermodynamics and using these relationships, ideal gas law, work definition, etc. If you have any question, as per usual, just leave them down below. If this video helped you out, consider liking it, and we'll talk soon.